Cool, yeah. So we're moving into the exploratory data analysis, and I will reiterate what we've done before with labeled data with supervised algorithms is the purpose, the reason for being of Explore is to understand what's driving the target, right? Even if we don't have a target variable per se, we still have goals, right? We still have things we want to learn, things we assume might be true, things we think the universe would be upside down if they weren't true, right? And we're trying to figure out what's the signal, what's the noise, and what's the relationship that signal is telling us. So to situate things, clustering is unsupervised. So we do not always have at least algorithmically, we don't have a target variable with clustering or unsupervised learning. But you'll see that what we'll do in this module is we will use the modeling for a couple of different tools. We will actually use the modeling to help us explore the data more fully. And so our entry into that, our entree, is this Explore lesson. Maybe today, maybe tomorrow, we'll get onto the modeling lesson after some exercises. And then after that, we will get into using clusters. So our goals of exploration, figure out what kind of patterns can you see? What are the signals in the data? What features are driving the outcome? And are there features we can construct that have better or stronger relationships? Of course, we use visualization tools and statistical testing and Explore. We want to walk away from exploration with some modeling strategies, some feature selection, some algorithm selection, an idea of what's our target metric and why, right? And it's all about finding the signal. So the agenda for today is 3 steps. 1, wrangle the data. Acquire, prep, summarize, split, identify questions to answer, hypotheses to test. And I don't know why this last bullet point's empty. It's answer those questions. If you can, right? If you have any evidence that supports an answer, then use that evidence. If you don't have any evidence that supports an answer, then reporting that you don't have sufficient evidence goes a long way, right? Let's say you run a project and you run 1,000 t-tests and you fail to reject the null 1,000 times. What can you say? Well, you can say that you don't have enough evidence to reject the null, and evidence supports evidence seems to support the null hypothesis. Right? So, yeah. Let's step into this scenario with this MAL data. This MAL data really is the hello world of clustering data sets, but we want to use the attributes of customers to estimate their spending score. And we want to target customers that are most likely more profitable, right? So our target variable in this example is spending score. Again, just because clustering doesn't have a target variable in unsupervised learning doesn't mean that your project won't, right? Really, it's what we want to explore here. So currently, all that we have is age, annual income, and gender. And it might be possible that we don't have enough data to build a model, or maybe we could do some unsupervised learning and find some clusters in the small data, and that will help us. And be useful. So let's jump right in. We're going to ignore some warnings, pull in pandas, NumPy, sklearn, SciPy for our statistical tests, matplotlib, Seaborn for visualization, and we're going to set some options on our float formatting. So let's go ye forth and talk to the database. Y'all just did this. Get a connection, select star from customers, and set the index to customer ID. Because customer ID is not a feature, it's an index, right? It's a unique identifier. And we'll get that data. So it's not terribly complex. We have gender, age, annual income, spending score. And in order to properly encode our categorical features, we'll run get dummies on that gender column. And so we're dropping the is female, and we are left with the is male column. 1 is a true, 0 is a false. So we're ready to get to know this data a little bit further. We'll run info on it. We don't seem to have any nulls. We seem to have some spread, right? The mean, or I'm sorry, the mean average annual income is 60. I don't know if that's dollars or percentage. I'm thinking this is probably between, well, no, that might be dollars because the max is $1.37 there, right? So we're getting to know things a little bit. Standard deviation is 26 on the annual income. Spending score seems to go up to, but not including 100. So I think spending score is some sort of index. And then Ismail is a binary column, at least in this data set. So we see that that comes up. We don't seem to have any missing values. We're all numeric. The outliers are not too extreme here. So now's the part of the episode where we can split and do some exploration. So split into train, validate, and test. And then the exploration process, when you belly up to the bar and say, okay, everybody, I'm gonna do exploration, what that means is you sit your happy self down and you ask some questions and you write them down. If you don't write things down, you're screwing around, right? Right? That's the difference between science and messing around, is writing things down, writing what you find, writing what you assume, right? So ask those questions, answer them with visualizations and statistical tests, and then summarize. Always summarize in English at a high level, even if your audience is technical, and especially if your audience is technical, just summarize it for them. Summarize it for them. They could be coming in hot from being, 20 layers deep in some other technical problem, and you're asking them to change gears to your technical issues. No, just summarize it for them. Again, even for a technical audience who can write the code that you're writing, it's still nice, because otherwise you're forcing somebody to context switch. You'll ever notice this really weird feeling when you're in the middle of Python and you realize you got to do something in SQL and you drop back into SQL? Is that jarring sometimes at all? Yeah, imagine if somebody else was working on another project entirely and they roll into yours and you just don't summarize what's going on. So don't make it extra work to understand what the heck you're working on, right? That's why we summarize. So we summarize at the top of our notebook, we summarize at the end of every section, top of every section, whatever it takes. A couple of tips and for visualizing for exploration, as opposed to visuals for your final product. Your charts, you can make a whole bunch of them. Crank them out in loops if you need to. Your axes and your labels, you clean those up later. Again, this is for your initial exploration. Color and size, we want to use those for information, not aesthetics. So don't get too fancy if most of the stuff is going to end up on the cutting room floor anyway. Keep it real simple. Box plots, heat maps, histograms, density plots, correlation plots. Titles are useful, right? But when you're building visualizations for you and you're the audience, it's okay if you don't have all of your axes labeled and everything perfect. Polish those up a little later. Let's take a look at some questions we might ask about this. Okay, so if our target variable is spending score, what are some things that we can test? What's the distribution of each variable? Does the spending score differ across gender? That's our one category. What's the relationship between spending score and annual income? Is it linear? Is it curvilinear? Is it discernible? Or is it just random? Oh, we don't know yet. What's the relationship between age and spending score? Is it linear? Does it serve a curve? Is it logarithmic? What's going on? And if we control for one variable, like age by decade, does spending score differ across annual income? And if we control for annual income, we'll talk about this language in just a minute. If we control for one variable, does spending score differ across age decades? So let's take a look at some of our first code here. What's the distribution of each variable? This one's real easy. For call in dataframe.columns, just barf up a histogram, right? We notice age is not normally distributed, neither is income, neither is spending score. And it's like a 65-45 gender split, it looks like. So spending score, it might technically be kind of normal-ish. Age and annual income have a bit of a skew. Because of that skew, instead of, let's see, we'll use Spearman's correlation instead of Pearson's, because these aren't, annual income and age are not normal enough. So we'll use Spearman's instead of Pearson's correlation test. And really what that means underneath the hood is that you need more signal from your data points to get a lower p-value, right? If you run a Spearman and a Pearson's R on the same data set, your Spearman's will most likely have a lower p-value because it's the burden of proof is not as high. The burden of proof for a Spearman's correlation is higher because it's non-parametric. Let's see, if we make some bins, we might want to bin for high salaries like 90K plus or minus 90K or based on age. Why would we bin salary based on that number or age based on that number? There's nothing specific in the data suggesting that, but we might make human cultural assumptions, right, about age, or human cultural assumptions about income. Yeah, question from Arsene. Go ahead, Arsene.
Yeah, you talked about doing a Pearson or a Spearman's correlation. Yeah. So is it useful to run one after the other? Because, okay.
No, you just make more work for yourself.
Okay.
We are specifically running Spearman's on age and spending score. Let's see, age and annual income, at least here, because they are a bit less normal. Spending score is a little bit more normal. We could use this on all three, but yeah, you don't need to make more work for yourself, Arsene. Please don't do that.
So your judgment call on the shape of the histogram is all you need.
Yeah. And if I have a lower p-value from a Spearman, if somebody happens to roll around and do a Pearson's R, I'm going to put more stock in the Spearman's because it's non-parametric. But yeah, you don't have to do both. Does that address your question, your concern there? Okay, cool. Making bins, again, is usually a human knowledge endeavor. Sometimes the bins are evident from the data itself, right? Some folks in the Zillow project found that the data seemed to suggest that something changed in home building in 1962. Some other folks used domain knowledge, World War II, right, instead. So sometimes the data gives you a hint on what you might bin on or group on. Other times, social aspects and cultural information gives you that. Okay, so the first question outside of looking at distributions, does spending score differ across gender? Easiest way to crank this one out, make a box plot, right? Make a nice little box plot where your X is male in this case, and the Y is the spending score. So your spending score is numeric. We'll go from 0 to whatever the highest spending score is, which is 99. And what do y'all see about these two box plots? What are some of the takeaways? I want to have a little bit of a discussion about this. So what are some of the things leaping off of the screen at y'all?
Exactly the same. It's close. Maybe off by a small.
Yeah. You mean this bar right here, right?
Yeah.
So that is going to be our median in a box plot. Yeah, that's okay. So we have identical medians, which is really interesting, and we have nearly identical third quartiles. It's off by just a smidge, but the first quartile is a much different story, right? Yeah, the range for the women customers is a lot higher. for that first quartile. For whatever reason, that means that, gosh, nearly a quarter of the male customers in this, in the mall are buying lots of bubble gum and jelly beans and marbles and little small items, I guess. I don't know. We have about identical whiskers here. And this does seem to call for a deeper investigation. The medians are basically the same. The first quartile is off. The third quartile is just about on top of each other. So what do we do in a scenario like this? What do you do if your visual on a box plot between two categories, two populations, seems to suggest, hey, buddy, it's time to run a stats test. What stats test are you gonna run here? T-test. What kind of T-test? Two-tailed T-test. Why two-tailed?
Let's see if there's difference.
Yeah, we'll see.
High, low.
Yeah, higher or lower, and we're not necessarily going for direction. Higher or lower is fine for a two-tailed. What other kind of thoughts on a T-test here? Two sample. Why? So to follow up on Andrew's two sample, why might we do a two sample here? Two populations. Bingo. Two populations. The population of all non-males and the population of all males in this data set. So we're not comparing a subgroup to the entire population. We're comparing two populations of the total, the population of non-males and the population of males. So yeah, this is a two sample, two-tailed T-test, and we'll compare spending score on male versus not male. I'm going to introduce something in the 3 minutes right before lunch. We'll talk about it when we get back from lunch. So we have two groups. We want to compare continuous variables across an independent sample, across independent samples. And our null hypothesis here is that the means of the spending score are the same between males and non-males. Now, we don't know, off the top of our head, we don't know if the variances of these two populations are equal. And so that's what this Levene's test is telling us. To test the assumption of equal variance, since T-test is assuming equal variance, we're going to add a layer of complexity. I think y'all can handle it now. If you want to freak out and go to lunch, eat lunch, then come back and relax. We're introducing a new statistical test called Levene's test. What this tells us is if the variances are equal or if they're not equal, okay? So let's read this. As in other hypotheses, the null hypothesis is one that assumes equality. Okay, so Levene's test has a null hypothesis, right? That the variance of those two groups is the same. Levene's test has its own p-value. So if our p-value is greater than 0.05, we'll say that variances are not statistically different, significantly different, excuse me. And we'll use that equal var argument on t-test, the t-test function, set that to be true. If the p is low, we reject the null hypothesis and we say that the variances are not equal. And this informs us to set the equal variance argument on the independent t-test to be false. It changes how this is going to operate underneath the hood. So the first things we'll do is run a nice little Levene test and send in the spending score on each one of our two populations, our non-males and our male customers. And we're comparing the spending score. So that's what Levene is spending here. And we see a p-value that's pretty darn high. And so this tells us that there's sufficient evidence to support the claim that the variances between these two populations are the same. They're good enough. And so why, real quick before we go to lunch, why did I run the Levene? To tell us if, when we run the t-test for independence, if the equal variance argument, we set that to true or false. That's it. I realize we're butting up right against lunch, so go feed your bread, go feed your mind. We'll come back and we'll pick up right where we left off, folks.